Good day to you all, wherever you are. I hope you're well and surviving the extended lockdown that we've got here in the UK. I expect, like me, you're looking forward to the vaccination. In fact, I've just had my first one. So I hope you all follow on behind me. For those who don't know me, I'm Alistair Scott, a past president of the Society. But now, as chair of the events committee, I try to keep all our events and activities going. And I'm always on the lookout for interesting and forward-looking talks. Welcome to this, the British Interplanetary's 14th live-streamed evening lecture since March and April of last year. As I said last time, we've got a lot planned for the rest of the year. We've got our big Beyond the Moon symposium on the 12th of April, Cosmonauts Day, which will have to be virtual. The call for papers is still open, so if you've got any ideas, please get them in. However, we are still hoping to run our Reinventing Space conference on the 28th to 30th of June as a face-to-face conference with the required social distancing in the QE2 Conference Centre in Westminster. I'm afraid the call for papers closed on Monday, and the details are on our bis.com or bis-space.com website. I'll try and tell you more about that at the end of tonight's lecture. Today, we're again using Crowdcast for both the presentation and the Q&A. It worked well last time, so let's hope we have a trouble-free session tonight. If you've enjoyed this evening and want to make a small donation, please click on the donate button at the bottom right-hand side of this page. Every little helps to cover the cost of these lectures. Please use the question system to ask your questions anytime during the talk. And as most of you know, you can always vote for those questions you want to hear by first clicking on the vote button. I'm pleased to say that we have an excellent speaker here with us tonight to tell us all about ESA flight operations. I first met our speaker at the IAC in Toronto back in 2014 when we announced the Rosetta team as winner of the Sir Arthur Clarke Industry Project Team Award. And he, as leader of the ESA Mission Control Team, came to meet us at our stand in Toronto. I won't say anything more, but we'll hand over to Fabrizio to do the introductions. Over to you, Fabrizio.
Yeah, thank you, Alistair. Can you hear me well?
Very well, thank you.
Thank you. Thanks a lot. And welcome to everybody. It's a real pleasure this evening to be able to introduce Paolo Ferri that unfortunately didn't meet when I had a very short stint in the Mars Express team just before launch, actually during the commissioning of Mars Express, but we share a little bit the same room because the Rosetta operation were also managing the same environment, the Mars Express environment for some time. They were split in two. And Paolo has had an outstanding career. He's not comparable to anybody else, in my opinion. So he started as an operation engineer, like many of us would like to do, participating in a flight control team as operation engineer, expert on some systems and knowledge of other systems. And then he went to work on the Eureka mission, on the clusters, on the Rosetta. He was flight director of both of Rosetta, Venus Express, and Goce. 3 different missions, 3 milestones of the European Space Agency, including, of course, overseeing also Mars Express, for example. So we are talking about all the important mission of the European Space Agency in interplanetary space. And he then became head of mission operation for the European Space Agency, and he had his say, let's say, on all ESA robotic mission operations. And Paolo just retired from ESA after his successful career, and he has an incredible view of flight operation because he also has been, let's say, an important actor in upgrading and in building the common system that we are using today, which is extremely advanced. The ESA system is extremely advanced compared to what is used by other missions. And Paolo recently also wrote a wonderful book. I'm showing this. This is unfortunately Italian. And in this book, he tells about his experiences. This is the first known book, very well detailed, and for any reader, which all the fantastic world of flight operations in space is told. And unfortunately, now it is only Italian, but we hope for an English translation very soon. So I made a very long questions. Before starting, I would like to welcome everybody on this lecture to join us later for a get-together on Zoom. We will provide the link later, and to follow the landing of Mars 2020. This is a very special evening to do this kind of lecture because we are talking about flight operation in deep space, and we are going to witness these fantastic events from NASA on Mars. And so after the lecture, there will be a Q&A session. Then we will disconnect from Crowdcast, and then we will reconvene a little bit later on Zoom, the link we will provide. I hope you will be able to join us because we will have different people talking, maybe explaining things, and it's a fun way to be together. Okay, so Paolo is to you now, and good luck.
Thank you, Alistair. Thank you, Fabrizio, for this opportunity. I'm very glad to be here. Thanks for the introduction. I think you raised the expectations of the audience with all those words.
Sorry, Paolo. I didn't mention everybody that Paolo is also a BIS member, of course, and this is very important.
Yes,
we are very proud of this, of course.
Of course, yeah. I hope you can see my screen.
Okay.
Can you see my screen shared?
It's not in presentation mode yet.
Okay, should be coming
I
now.
see the screen, not in presentation. Okay, now it's in presentation mode. I see this correctly.
Very good. So this is my entering slide. I will talk about the history of ESA operations, which I accompanied for the last 36 years. And this history is not much longer. In fact, when I joined the European Space Operations Center in Germany, it was only 17 years old. And now, of course, it's over 50. Just 2 words on the European Space Agency. I suppose most of the audience is very familiar with our agency. 22 member states, of which the vast majority are EU states, but not all EU states. There are very important states which traditionally are with ESA and were not with the EU, Norway and Switzerland. And okay, I have to list also the UK now as a non-EU state member, very important member of ESA. There are other cooperation states, associated members. I mean, it's a very nice and large international organization. And it deals with a lot of activities, as you see here, from science, one of our, in fact, our core program, to human spaceflight, exploration, Earth observation, space transportation, navigation, and telecommunications. These are the programs. And then it has 2 areas, which are technology and operations, which are the support areas. And I put the big arrow on operations because that's what we're talking about tonight. The sites of ESA, there are many, of course, the main sites all in Europe, but of course other offices and ground stations around the world. And again, the center of the world from the aspect of operations is our control center, the European Space Operations Center in Darmstadt, which is south of Germany near Frankfurt am Main. The center deals with 2 main areas. One is really mission operations, so preparing and executing all operations of all the robotic missions of the European Space Agency. The other area is ground segment engineering, so dealing with all the aspects of the technology and the infrastructure that we need on ground to operate our missions. Typically, ground stations, you have this beautiful picture here on the right-hand side, computer, communication lines, and so on. What is a ground segment? You see this is a slide I use in many training courses. It's basically 3 main blocks. There is the Mission Operations Center, which is here a big block, first of all, because I see the world from this perspective, but also because I will show you a bit more. I needed space to show more details in there. There is a communication network and there is a ground stations network. The antennae are all around the world. And behind the operational ground segment, there is, of course, all the aspect of dealing with the payload, the the network of centers or of actually end users which are behind a space mission depends on the type of mission, of course. And of course, in space, you have the satellite. Inside the Mission Operations Center, we have important building blocks, which this is ESOC terminology, but it's quite well spread. The heart is the mission control system, is the computer system that actually decodes the telemetry and encodes the commands, so actually talks to the, or allows the human beings to talk to the spacecraft. A system dealing with the network operations, because from here you have to operate not only the satellite but also the network of ground stations. The mission planning system, which is getting more and more important in missions, and more as long as missions are getting more and more automated and offline operated, most of the operations actually take place at the planning level. Flight dynamics, fundamental system which deals with the orbit determination, maneuver preparations, with attitude control, all the aspects which are dealing with the dynamics of the spacecraft. A set of simulators to train the operators, to validate the procedures. And okay, this is very ESOC specific, but it's a system that isolates all the operational systems, the data disposition system, to talk in a secure way to the outside world, to the users. This is a picture of the control room, the main control room in the control center in ESOC. There are many others, but we're very proud of this place because this is actually the room where we execute the critical operations of all missions, typically at launch, but also, of course, especially for interplanetary missions. There's many other critical phases, arrival at planets, landings, and so on. And this is the place where we gather every time there is a critical mission phase. And this is the place where our people have actually made the history of space flight in Europe. Mission operations is basically not very different from operating a toy car or doing these other things like controlling during a race, a Formula One car, or even sitting in the cockpit of a modern aircraft and controlling all the other elements of this aircraft. What it makes the difference is the complexity in terms of number of telecommands, so instructions you can send to the satellite, and telemetry parameters, which is information you get from the satellite. Like in this case, your toy car is the satellite. You don't get any telemetry because you have a visual contact. In case of Formula One cars or all the systems of an aircraft, of course, the number of parameters increases. I suspect since I first created this slide, even this is increasing dramatically. When we come to a complex satellite, in this case is the Bepi Colombo probe here, we are talking about more than 10,000 different telecommands and more than 100,000 different telemetry parameters. Another addition to complexity, especially in case of interplanetary missions, but also for some other missions, at least this aspect apply, is that you are in a control center, but the machine you're operating is far away, is not next door, like when you're doing a testing of a satellite, which is very similar job to the one we do, but the satellite is next door. And maybe when you go home in the evening, you can switch it off and switch it on the next day. Here, the satellite is always active, is flying, and is not flying next door, is flying at millions, hundreds of millions of kilometers from you. If it's around the Earth, it's only a few hundreds of kilometers, but it's still remote. And even the communication methods or the tools you have to communicate, the antenna, they may be at thousands of kilometers away. So you have to operate the satellite, you have to operate the antenna, which are very complex systems as well, and you do it from remote. Talking about the history of ESOC, in fact, before ESOC became a control center, 1966, it was a data center, but what we would call today a data center or a computing center. And this is taken from a newspaper from that time, which says in German, 300,000 Grundrechnungen pro Sekunde, which is 300,000 basic operations per second, which probably every kid would laugh today about this computing power, and you needed a full room of machines in order to do that in 1966. The data center was converted into a control center in September 67, and only a few months later, in May 68, the first ESA, at that time it was not ESA, it was the precursor of ESA, it was called ESRO. The first European satellite was launched successfully. You see the size of these satellites. They're really, today we would call them probably a mini satellite, a few tens of kilos. And it was a scientific satellite in a relatively low orbit around the Earth, ESRO 2. This is how the control room looked like at that time. Mainly analog, lamps here, telephones, very little telemetry was coming in real time. The majority, for example, all the scientific data would be collected at the ground stations around the world, stored on tapes, and then ESOC people would actually travel to those remote places to collect the tapes and get the telemetry back. What was flowing on communications lines in real time was really very, very limited housekeeping telemetry, so engineering telemetry. I make a first jump because the first years were all dedicated to similar satellites, relatively low Earth orbiting scientific satellites. But in 1975, you can see that we had already launched a number of satellites, 10 satellites, and we were going into the next generation of satellites, which were the geostationary satellites. So it was the first time with these telecommunication and meteorological satellites that we were preparing to launch and jumping into from low orbits into something, a new field for us. The network of ground stations were still being built up, but we were moving into a network of what we call today near Earth antennae for again operating satellites which are in Earth orbit, and they are 50-meter antenna. Here you see the antenna at the Vilafranca tracking station in Spain near Madrid, and we started in that phase to specialize on geostationary satellites. I don't have to explain what a geostationary satellite is, but what is important in order to rotate at the same speed as the Earth and therefore be, as the word says, geostationary over the sky, we had to put it on a very far away orbit from the Earth. From the center of the Earth, you have to go to about 42,000 kilometers in order to have the same speed of the rotation of the Earth. And there, the technique, which is a very basic technique, which is called Hohmann Transfer, was adopted for the first time in ESOC. So you were on a low Earth orbit, you would activate an apogee motor. Well, first of all, you would burn here. Either the rocket would put you on an elliptical orbit, and then you would only activate the apogee motor to circularize it, or you would be on a low orbit and you activate the motor twice, here to increase your apogee, and when you would be at apogee, you would burn it again to circularize. This is a very simple Hohmann technique, but at that time we were experimenting it for the first time in Europe. After a few years of geostationary satellites, we became pretty familiar with telecommunication and meteorological satellites. And another important jump in our history was Exosat. Not only because it was the first satellite I worked on, I arrived in '84, but because it was the first scientific satellite on a highly elliptical orbit, which would bring it to an ideal position to observe the sky. Exosat was an X-ray astronomy satellite, but also was the first satellite with a reprogrammable onboard computer in Europe. And this was a complete revolution. At that time, satellites would fail, the hardware would fail, would start failing immediately after launch and keep failing throughout the mission, which would last maybe 1 or 2 years, not more. Exosat didn't make any exception. When I joined the team 1 year after launch, basically all the redundancy was gone, half of the payload was failed. This was normal at that time. Industry was still learning how to build reliable space hardware. But in this case, we had the opportunity to at least work around some of these problems with the software. The computer was installed on the satellite in order to do data processing of the scientific data, but we used it in various occasions to actually work around problems with the onboard electronics and actually save the mission. I mentioned the highly elliptical orbit. This was the ideal orbit for telescopes at that time because on this orbit you're actually relatively slow, of course, when you're far away. These are Kepler's laws. You're slow when you're far away, the second law of Kepler, and you're very fast when you're close to the pericenter. And this allows the satellite to spend most of the time far away from Earth, so it can do nicely sky observations without the Earth in the middle. And the orbit of EXOSAT, just as an example, was a 4 days orbit, and we would spend in this disturbing area, which was not only disturbing because of the Earth in the field of view, but also because we were getting into the radiation belts, so we had to switch off our instruments. Only a few hours per orbit, and we would spend more than 3.5 days every orbit in observation time. The control room at that time looked like this. Again, we had computers with alphanumeric displays, black and white. The telemetry that EXOSAT was downlinking was only a few kilobits per second, and we would display the main parameters on these fixed wall displays, all handmade. Yeah? Every parameter was hardwired to its own position. Yeah? The workstations as well, they had basically handmade buttons for specific functions. So the keyboards were made for the mission. And only the scientific team, to which actually I belonged, had a sophisticated computer that would do graphics and even color graphics. And we also on ground, like we did on board, very often the flight control team and us, I was in the science support team, we cooperated to use the ground computers for the science to help the operations of the spacecraft. The next jump in our history, next milestone, is the first real interplanetary mission. Giotto, launched in 1985, together with a fleet of other probes to encounter the comet, the nucleus of Comet Halley, that comes back every 76 years. And this time was the first time Halley would come back during the space age. And of course, we couldn't miss this opportunity, although the space age was pretty young at that time. And Giotto was sort of the admiral of the fleet, because was supposed to fly very, very close to the nucleus, while all the other probes were staying a bit more at a distance. There were Japanese and Russian probes. The mission was interplanetary, but as you can see here, this was the orbit of Halley's comet. Oops, sorry. And we stayed on a Earth-like orbit. So we launched Giotto on an orbit to encounter Halley here. By the way, it encountered it at a very, very, very high relative speed, 68 kilometers per second, because Halley happens to fly in the other sense compared to the planets. But we didn't go far away from the sun, and also, by the way, not too far from Earth by staying on a similar heliocentric orbit. So it was a first step into the interplanetary world, but by not going so far, we could even afford to still use 50-meter antenna, so relatively small antenna. We had to build one in Carnarvon, which is in Western Australia, because the main encounter was taking place in the Southern Hemisphere, and we wanted to have a place there, of course, to observe and get the telemetry from the main encounter. You see here the images collected by the camera, which show how ignorant we were at that time of what a nucleus of a comet is. We thought, the scientists thought, that it was a bright object. And as you see, the camera was programmed to follow bright objects, but the nucleus in fact turned out to be extremely black. In fact, one of the blackest things you can find in the universe, reflecting about 5% of the sun light. But at that time, nobody had flown by the nucleus of a comet. Nobody knew what it looked like. Anyway, Giotto was our first step into the interplanetary world, but it would take another, well, basically 20 years because we would really get into real interplanetary missions. We are coming to that. In the meantime, there were other very, very interesting experiences. This was the first experience, and in fact, for the center, the only experience with human space flight. We launched with a space shuttle in the 90s, launched and retrieved with the second space shuttle a platform called Eureca, European Retrievable Carrier. It was a microgravity platform, supposed to refly 5 times, eventually flew only once for various reasons, but it was an incredible experience. I had the luck and the fortune to be in this team. The spacecraft was a very, very innovative, very future-oriented spacecraft. Basically, in this spacecraft was invented what we use today on every spacecraft, packet telemetries, OBCPs. This was the first pioneering spacecraft in that. But unfortunately, the spacecraft was still belonging to the generation of spacecraft that fail continuously. So we flew for 11 months, and it was a continuous trouble. This was the control room that you see was already evolved with color screens, but still fixed screens, fixed displays per screen. So when you wanted an alphanumeric display, it would occupy the full screen. Nowadays, we can put on a screen 20 or 30 windows, and in fact, we cannot find even what we're looking for. At that time, we had to be very disciplined with the usage of the screens. The problems with Eureca started soon after launch. In fact, we launched, and 12 hours later, the astronaut on board, Claude Nicollier, the ESA Swiss astronaut, operated the robotic arm to pull us out of the satellite, of the cargo bay of the shuttle. We were supposed to then release the spacecraft, so activate it. We were activating it using a link through the shuttle cargo bay. There's a little antenna here on this side, and we would talk to our spacecraft via this antenna and via the shuttle network. But this link had a problem, a compatibility problem, which if you are interested, I can explain the details afterwards. But this compatibility problem caused continuous interruptions both ways, and this was a complete disaster. We were totally confused. We didn't know why this problem occurred. This was not discovered in tests before flight. And so we were caught totally by surprise. We had to rush into the deployment of the arrays because the batteries were running out. And in fact, we deployed them against all the flight rules in sunlight. It was totally forbidden to deploy them in sunlight, but it was our only way to get the spacecraft survive. And we deployed them by commanding Eureca from the ground, using our ground stations, because the communications via the shuttle were not working properly. Once we deployed the arrays, we had more time, so we took the night to think about it, and the next day, eventually, Eureca was released. Here you see a fantastic picture taken by the shuttle astronauts of Eureca flying over the Earth. This doesn't mean that the problem stopped. We had other problems already in this phase that delayed the maneuver to raise the orbit, and the problems continued throughout the mission. Just to give an example, after 11 months, we had lost 2 gyros out of 6, 3 payloads out of 12, 40% of the solar array. This was quite normal in those times. On the retrieval shuttle, the new shuttle flew to catch us. We came down with the orbit, and we did a rendezvous with the shuttle in 1993, June, July. In fact, the end of the mission was 1st of July. So caught us very nicely. You see the spacecraft here. We managed to retract the arrays, retract the antenna. But of course, this was too easy, and the spacecraft decided to play another trick there. The antennae were retracted, but the latches that were supposed to block the antenna there didn't work, because the antenna didn't really reach the point of allowing the hooks to engage. We had again to park overnight, and then we asked an astronaut to go out, do an EVA, and he was put with a robotic arm close to Eureka. You see here Eureka in the cargo bay. And while we were sending commands to reactivate Eureka and get it ready to latch, we told the astronaut to push with his fingers, push against the antenna, push in this position. And then as soon as he started pushing, we could send the command to latch, and this worked. This was another very exciting moment. Again, double failures. There's so many things that I could tell about Eureka, but I think I would need a presentation just on its own about this mission. In the 90s, in the mid-90s, the control room, you see it here, still the wooden cover on the walls, the big screens, but the wall screens, but you see the room was increased in size because we wanted to fly the cluster fleet, 4 satellites to be launched for the first time together with the Ariane 5 on the maiden flight of Ariane 5. So we needed, each satellite had 2 controllers dedicated, a spacecraft controller and an engineer. So we had 8 in front, and then we had the operations manager and another central position here to oversee the full fleet. Unfortunately, 37 seconds after launch, this is what we saw on our screens. Ariane 5, again, due to a set of really unlucky circumstances, but basically software problems, exploded 37 seconds after launch, 4 kilometers altitude. That was the end of our mission. It was a very dramatic moment, which I will never forget. I was sitting in this position at launch. It was the first mission I was responsible for. But overall, it had a happy end. The cluster was rebuilt, relaunched in 2000, and it's still flying out there, although it's a very old mission. But and it has lost batteries, lost a lot of things, but it's still working pretty well. Those were the years when Ariane 5 then started working properly. Those were the years where we launched other telescopes. XMM, again, was a successor of Exosat, so X-ray telescope, and Integral in the gamma rays. 99 XMM with Ariane, and 2001 Integral. This was with a Russian launcher. These were the last satellites we launched, so space telescopes we launched on a highly elliptical orbit like Exosat. And they indicated the turn of the big change in expertise in European industry. So while the satellites built in the 80s and the beginning of the 90s were still having a lot of failures, experiencing a lot of failures in orbit, these things were launched at the end of the 90s, and these things are still working now extremely successfully. XMM is today the oldest spacecraft we have been operating, still extremely healthy. It had a couple of issues, of course, but it's working marvelously. In the meantime, we were really equipping our infrastructure for interplanetary flight and for science missions of the future with very high data rates. It meant building big antenna, 35 meter. And the first one was inaugurated in 2001 in Norcia, also in Western Australia, an ideal position in the southern hemisphere. These antennae are extremely complex machines. From a mechanical point of view, you see these are monsters, 600 tons, which had to be pointed with a fraction with an accuracy of a fraction of a degree. Inside, they have high technology, cryo-cooled amplifiers and equipment, maser clocks, and the optics. So the optics for the radio, for the microwaves, they work like a telescope. Yeah? So the signal comes, is reflected by the subreflector here into the antenna, and through other mirrors comes down to the equipment, the receivers and the transmitters. The antenna was built mainly with the argument of following the Rosetta mission, which was in preparation. But Rosetta was delayed from January 2003 to March 2004. And therefore, the first spacecraft that actually used this antenna, and in fact helped also debugging our initial unexperienced operations, was Mars Express, launched in June 2003. Was the first real interplanetary mission to another planet, first ESA mission that reached another planet and entered in orbit around it. And again, now, like XMM, I was saying before, a satellite built in the late 90s, beginning of this millennium, and still working super efficiently and super healthy and productively at Mars. Mars Express carried, so first of all, went to Mars with the Earth-Mars Hohmann Transfer. So it's the same principle as around the Earth, only you start from the Earth orbit, you do a push, you go into a Hohmann orbit, which is a transfer orbit. When you get at Mars, you have to do another maneuver, and you do it by actually using the gravity of Mars that captures you, but then you have to brake in order to avoid that Mars then uses, sends you like a slingshot again into deep space. Mars Express carried a British lander, which was the first European attempt to land on Mars. This is a picture we took with our visual monitoring camera of Beagle 2 that was leaving the spacecraft. And it was planned that Beagle 2 would only transmit once arrived on Earth. And once arrived on the surface of Mars. And unfortunately, when it arrived on the surface of Mars, it wasn't able to transmit. And we didn't know anything until only very recently, if I'm not mistaken, 2015. A NASA orbiter managed to spot the parachute, the rear cover, and Beagle 2. And in fact, enlarging this picture, you see the Beagle 2 was actually pretty healthy on ground and managed to partially open, but not fully, and that's why it could not transmit. It was a shame, of course, but we have learned from this that during this very critical phase, that, by the way, tonight we're going to leave again with another NASA lander, during these minutes of terror, you need to have a radio link active. Otherwise, you don't learn. You don't know what happens if something goes wrong. Mars Express, as I said, is still in orbit, doing a complete mapping of the planet, working as a relay orbiter as well in many occasions, and a very successful mission and very healthy. It went through two big crises, one with the mass memory, I think, if I'm not mistaken, 2007, and one very recently with the gyroscopes. Practically today, the gyroscopes are laser gyroscopes that are getting very old. And today we operate Mars Express practically without gyroscopes, and we are very proud at ESOC because this software development and complete change of procedures and approaches was all done in-house. The spacecraft was not built to operate without gyroscopes, but we managed to do that. Of course, now I have to talk about Rosetta. I will talk in two parts of my presentation because the mission was very long and other things happened in between. But I can't avoid giving some details on Rosetta. This has been part of my career for 20 years, a very important part of my career. The launch was in 2004, so after Mars Express, and it had a 10 years travel. The first mission to rendezvous with the comet. So differently from Giotto, differently from all the precursor missions, it was not flying by a comet, so staying just in the proximity for a couple of hours, but really getting onto the same heliocentric orbit of the comet, and therefore flying in formation around it, orbit it, and staying in the proximity for almost 2 years. In fact, more than 2 years eventually. So 10 years travel, we did 4 gravity assists, 2 asteroid flybys. We reached record distances from the sun at that time with solar arrays. Nobody had been so far from the sun with solar arrays. And also 1 billion kilometers from the Earth. And the end of the mission, so the arrival at the target was in 2014. We carried a lander and we had it landing on November 2014, and then we finished in September. But I'll tell you about the late phases later. What I want to tell you is why the trip took so long, and we used the trick that in interplanetary flight is used very often. So we use the gravity of the planets to accelerate our spacecraft. You see the Earth, 1 year later, the Earth was used to accelerate. We are in a higher orbit here. Then we use Mars to come back to Earth and get another gravitational kick here in 2007. You see the orbit has a higher dynamical energy, and okay, we crossed the asteroid belt, so we had a couple of flybys there. You see the comet there, but it's not important at this stage. Important is that we got the third kick from the Earth, and now we have the right velocity. Okay, crossed again the asteroid belt, and the right speed to catch up with the comet and get to a rendezvous. We were getting at this stage so far away from the sun that we had to hibernate the spacecraft, switch it off for 2.5 years. But 2.5 years later, and 10 years after launch, in January 2014, we were there, and the mission could continue. Gravity assist, I said we use the gravity of the planet to accelerate, but I just want to give you a little bit of detail because what I said is not really, say, physically correct. What happens when you fly by a planet is that you go in with a certain velocity. You get accelerated, yes, by the planet, but then when you go out, you get decelerated by exactly the same amount of velocity. So your velocity vector, the modulo of your velocity vector, is identical when you go in and when you go out. It has only turned your direction, but you have not gained, with respect to the planet, any energy, any velocity. What you actually do is you profit from the fact that the planet is moving around the sun, so it has its own velocity vector or momentum. And when you add, with respect to the sun, these 3 vectors, you realize that with respect to the sun, you're going in with this velocity, you're going out with this one. So you have actually had an acceleration, which we call the delta V, and it's a significant one. I mean, we're talking about kilometers per second here. You would need tons of fuel to give this acceleration to the spacecraft. So practically what we are doing, we're stealing a bit of the angular momentum of the Earth around the sun and giving it to the spacecraft. So if you have the impression that the years are getting longer, Rosetta is probably the reason, because we did it 3 times and now the Earth is flying slower around the sun compared to the past. But of course, this is a infinitesimal fraction of time. I said that other things happened during the flight of Rosetta. 2005, we landed on Titan. We're very proud of it, but it was not a real interplanetary mission for us, because the mission was Cassini, was NASA. They were doing the mission, and we were just a passenger. Huygens was released after 7 years of flight by Cassini, 5 days before passing by Titan, and then it landed on the moon of Titan, the moon of Saturn called Titan, the biggest one, very exciting moon. It was supposed to take atmospheric measurements and then crash, but in fact it did a soft landing and it could take even pictures of the surface of Titan. An incredible world where you have basically morphology of the surface, which is created and modified by methane instead of water, but it looks like similar to the Earth. You have rivers and lakes and even rain. Of course, this was the joy in the control room, but it was a very special mission, just lasted a few hours for us. Another interesting interplanetary mission we flew in those years was Venus Express. In 2005 was launched, arrived at Venus in 2006, was a sort of sister spacecraft from Mars Express, of course adapted to the proximity of Venus. It was our first mission towards the Sun for atmospheric investigations that you see some pictures on this left-hand side. A interesting mission of those years started in 2003 and ending in 2006 was Smart 1 to the moon, but the real objective of the mission was to test solar electric propulsion, so an ion thruster. And being a technology mission, of course, all the attention was on the utilization and also the operational utilization of this tool. But of course, it carried science instruments, and we stayed around the moon for a year and a half. Towards the end, we were spiraling down to the moon, and here I have to tell an episode. I had become responsible for Smart 1 only 1 month before, because that's in August 2006 I became head of the interplanetary missions division in ESOC, and Smart 1 was about to finish, and on a Sunday morning we had calculated that spiraling down to the moon, when it ran out of fuel, it would crash at 7 o'clock on a Sunday morning onto this hill here, about 1,000 meters high. Onto this hill here, this one here, 1,000 meters high. These orbits were 6 hours long, and on the Friday, an American scientist told us that he had better maps of the moon, and that we would actually crash onto the rim of this crater 6 hours before. This was, of course, a big alarm. We had invited all the VIPs, all the directors, maybe politicians as well, for Sunday morning, 7 o'clock, to observe the crash and the end of the mission of Smart 1. And we couldn't call it off. So we didn't know what to do until our flight dynamics people, who are fantastic and very, very creative people, they said, okay, we do not have fuel anymore to change the orbit, but we have cold gas for the offloading of the reaction wheels, so for the attitude control. So we use some of this cold gas to increase the altitude of the orbit by about 200 meters. So eventually on that night, on the Saturday night, we flew just a few hundred meters, maybe 100 meters over this crater, and then we crashed as planned on the Sunday morning. But it wasn't one of my best weekends, I have to say. I've spoken about flight dynamics, and here I have to give a little bit of technical details. I'll do it very quickly. This is the basic of orbit determination. You measure the distance by, we call it ranging, by the radial distance of the spacecraft from the antenna, by sending a tone and measuring how much time it takes to come back to Earth. You measure the relative velocity, the radial velocity, by measuring the Doppler shift of the signal. Doppler shift, you're familiar with it, is the same what your ears detect when you have a car coming to you. You hear the noise at higher frequency. When it goes away, you hear it at lower frequency. So by measuring the change in frequency, we can measure pretty precisely the relative speed. Of course, we can also measure the angular pointing of the antenna, but this is only a cross-check. It's not so important for orbit determination. When you're in interplanetary space, you can actually use the Doppler shift to measure the position, at least in one direction. Your Doppler shift has this type of form where this component is the actual velocity of the spacecraft with respect to the Earth. This component is simply the Earth rotation, because for half of the rotation, your antenna is going towards the spacecraft, and for the other half of the day, is coming back. So when you see that it crosses the zero, when it changes here, the slope, it means that you are at the meridian. So you have a pretty precise measurement of the position in the sky, at least in one direction. You can even improve the position measurement by doing a sort of interferometry technique. We call it delta door, so delta differential one-way ranging. Basically what you do is you measure with two stations. The further the better, but of course you cannot go too far away, otherwise you don't have the signal in parallel. You measure the signal in parallel from two stations, and you basically you calculate the arrival time, you measure the arrival time, and as you can see from this plot, the signal arrives first at this antenna and later at this one. So by knowing this delta time, you can measure the angle pretty precisely, the angular direction in the sky. Because the atmosphere is different here from here, and it affects the signal and the phase shift of the signal, which is actually what we measure, we do calibration by pointing to the spacecraft and to quasar, which are in the same direction of the spacecraft. So it's a very complex technique, but we're using it extremely successfully with our interplanetary satellites. Orbit determination is a very simple process in principle. You have a dynamics model with all the forces that you think are acting on your spacecraft. You put position and velocity as initial condition. What you get out is the predicted future conditions, maybe at tomorrow or in 1 week or in 3 hours. And these conditions you feed back as new initial conditions, and ideally this is working on its own. But of course you need a check with reality. So what we do, from the predicted future conditions, we predict the future measurements. We compare them with the actual future measurements, and if we call the difference the residuals. If the residuals are 0, then we are happy. The model is okay, the actual future measurements lead to exactly to these new initial conditions, your model is perfect, and you can continue. If they're not, then you have to update your model. It means that you have misinterpreted the forces, or not calculated properly, the radiation pressure, the drag, or whatever. And of course, you have to correct, this thing doesn't work anymore. You have to use the actual future measurements as new initial conditions. This process continues throughout the mission. And sometimes this process is used to detect an anomaly. What you can see here is an example of Rosetta where daily you see these are the measurements and they clutter around 0. This is the range rate, so the velocity. You see the units here are millimeters per second. So when the measurements are close to 0, it means that your residuals are 0. So your model is very good. Here is the position in kilometers, and again, when you're close to 0, it means that your model is very good. In this phase of the mission of Rosetta in 2005, we left it alone for the first time in a special mode, thruster mode, for 7 days. And when we got the contact 7 days later, we saw that the velocity compared to our predicted velocity, should go back. Anyway, the velocity compared to the predicted velocity was 2.5 millimeter per second too high. This was an enormity, of course. And of course, also the position was different. We took a pass a couple of days later while we were scratching our head, and we saw that fortunately the velocity was still there. So whatever had caused this jump didn't work, and it was not there anymore. So it was not a leak, which is a continuous. Otherwise, it would have increased the difference here. Of course, the position had changed compared to a measurement. Yeah. So it must have been something that happened only in one occasion. And in fact, we could draw this line and find out that something must have happened on this day, which was the 2nd of August 2005. We thought of micrometeorites, we thought of all sorts of things, but eventually what we did when we managed to get some recorded telemetry back was that in the day around the 2nd of August, we had an anomalous fuel consumption. This was the normal fuel consumption, a couple of grams per day. And our thrusters, do not have time to explain these plots in detail, but our thrusters were not behaving properly. In fact, one thruster for 3 days had decided to stop thrusting. And then it went back to thrust. We never managed to explain this problem, but we didn't have enough telemetry. So we installed more telemetry to detect it and diagnose it better in case it would happen again. It never happened again. So your Rosetta flew for another 11 years, and this thing was never reproducible. Nobody knows what happened in that case. The radio signal can help you also in other cases. This was an anomaly of XMM, where in 2008 we XMM near Earth orbiter. We lost the signal. We couldn't find it anymore. We tried all sorts of switches of the transmitter, check the station and so on, but we could not recover the signal. So we thought maybe the spacecraft has been hit by a debris, so we wanted to have radar and optical observations to find it. And they actually confirmed that it was okay. The spacecraft was there, it was not tumbling, it was there, nicely and flying. So the only thing we thought was that something on board, this RFDU switch, which is the switch that connects the transmitters and the receivers to the antenna, maybe failed, which was, considering the design, extremely unlikely. So after the radio and optical measurements showed that the spacecraft was there, those were the optical, these were the radio measurements. The radar measurements also told us that it was not tumbling, so it was very nice and stable. The only suspicion was this RFDU switch. Again, it allows you to swap the transmitter, so the transponder connected to which antenna, to go from this position to this position, and either use antenna 1, transponder 1, antenna 1, transponder 1, antenna 2, transponder 2, or cross them. This switch apparently had got stuck in the middle, and it didn't connect any antenna to any transponder. So what we did, we used New Norcia when the XMM was flying over it, and we shot well, first of all, we tried to detect a signal, and we saw a very, very weak signal using our radio science instruments, a very, very weak signal, but we could not command it. Then we knew that XMM would go at pericenter over Goldstone, a NASA station. So we asked Goldstone to shoot commands. And just a few hours later, Goldstone was able to switch again this switch, and we recovered XMM. So a case where your radio signal is lost is a case where you're totally lost. But eventually, with your deep space antenna, you can recover even near Earth satellites. In 2009, we flew for the first time, we launched for the first time our satellites to a libration point, a Lagrange point. You may be familiar with the Lagrange points, are say unstable equilibrium points in the Earth-Sun system, rotating system, of course. And ideally, you send a satellite around L1 to observe the Sun, and you send it to L2 to observe the universe, because you can point in this direction, the Earth is behind you, the Sun is behind you. It's wonderful. So we launched various satellites there, also LISA Pathfinder. This was not an observatory, but we sent it there because it's very nice and quiet also from the disturbance. LISA Pathfinder was supposed to do very, very sensitive measurements of movements, with these accelerometers, in order to show that we can detect one day in the future gravitational waves. So this was the trip to LISA Pathfinder to L1 in the direction of the Sun, and that was the final orbit. You don't actually stop at L1, you orbit around it, also not to be in the direct direction of the Sun, also to ease the communications. In the meantime, Rosetta was continuing. We did an asteroid flyby, and the flyby forced us to develop a new navigation technique, which we call optical navigation. You see, we took pictures of the asteroid, which is the thing that this little dot in the middle of the flashing circle, and measured the movement of this asteroid compared to the stars in the background. And this gave us a better measurement of of the position of the asteroid compared to our trajectory. This was the uncertainty we had from our radiometric measurements, and these were the uncertainties of the always better and better resulting from our pictures. So we saw that we were away from the target, so we did a maneuver, we continued. These are more enlarging this, more and more pictures taken, and eventually we did flybys with a very, very high accuracy. This optical navigation, of course, we used in the also in proximity of the comet, but we had to change that as well. In the meantime, we built new antennae, and we have now a deep space network of 3 antennae, one in Australia, one in Argentina, one in Spain, which give us a full celestial sphere coverage, and we're very proud of this network today. When Rosetta finally arrived at the comet, these are the pictures taken of the comet nucleus in the last few days before arrival. We had to first characterize the nucleus. This was a mission that to the unknown. We didn't have a clue of this nucleus. We knew more or less the size, but we had no clue, for example, of its mass. So we stopped at about 100 kilometers from the nucleus. We did these strange orbits, which called them pyramidal orbits, at first 100 and then 50 kilometers altitude, and then the distance. And then when we measured the bending of these orbits, by the very weak gravitational forces of the comet, we managed to conclude that we had a measurement of the mass of the comet. It was about 10 billion tons, and we could enter into lower and semicircular orbits. This went on for a few months until in October we went down to 10 kilometers orbits, and we were ready to deliver the lander. Just to give you an idea of the magnitude of these forces, this is the radiation pressure from the sun, and this was the gravitational force when we were at 100 kilometers, at 50, and it went up by 2 orders of magnitude only when we were very, very close, at 10 kilometers distance. Yeah? But we're talking about still extremely faint forces. And these were forces due to the drag from the gas and the dust of the comet. And this actually is simply the higher potentials of the higher orders of the gravitational potential of the comet. So the fact that the comet is not spheric actually induced forces, perturbation forces onto our orbit, which were of the same order of the other ones. We had to develop a new type of optical navigation because the comet now was not a dot anymore like the asteroid, but it was an extended object. So we had to select landmarks, make a digital model, and then compare pictures from one to the next, and in order to determine the relative position and velocity of the spacecraft compared to the comet. Later we developed image recognition software to find automatically the landmarks on the comet, while in the beginning all this was done manually, comparing the pictures. The day of the landing came in November 2014, pretty soon. This is the last orbit at 30 kilometers altitude with all the milestones of this orbit, the maneuver to dive towards the spacecraft and then towards the comet, then the release of the lander, which fell for 7 hours onto the surface of the comet. And as probably most of you know, while we were jumping and happy, and because we thought Philae was nice and solidly on the comet, Philae decided not to anchor itself to the surface and jump around. So we spent not 7 minutes of terror, but 2 hours of terror. And eventually from the landing side, which was there, it jumped to the other side of the head of the comet in this area here. We were lucky that we never lost the signal, so we could get all its pictures. We could get it to do all its first scientific sequence, which was planned to do with all the instruments. Of course, it couldn't work much longer because this place was very dark, so we couldn't recharge the batteries, but it was at least running its all experiments once, which was the minimum objective of the mission there. Rosetta continued for 2 years on its orbit, leaving with the comet while the comet was getting close to the sun, and then it was getting far away again. In fact, it's this direction here. And we had our problems there. The comet became active, getting close to the sun. You see this gas coming out. Sometimes you have explosions on the surface. We had to move away because our star trackers mounted on the back of the spacecraft were needed to see they had to see the star in order to help us with attitude control. But this is what they saw in the dust that the comet was throwing at us, like a snowstorm. They couldn't see the stars anymore. So here you see the profile of the distance between the comet and Rosetta, here at the arrival, the characterization, the landing, Then we started moving away, moving away. Here there was a moment where Philae woke up again, so we tried to come back, but we couldn't get closer than 150 kilometers. Then we moved away when the perihelion was here. And then when the comet got quieter again and again, we came back, we did another excursion just for scientific reasons. And finally, we were daring to get and land onto the comet. This is the signal disappearing onto the on the 30th of September 2016. This is the last picture we did. So the mother spacecraft landed on the comet, and of course this was a suicide landing at the end of the mission. Something that happened also in 2014 was an aerobraking test with Venus Express when it was getting close to the end of the mission. This lasted only a couple of weeks, but it was important in preparation for ExoMars TGO and Schiaparelli because we needed to do a proper operational aerobraking there. If I'm talking about ExoMars, I have to talk about first Schiaparelli, which was our next attempt to land on Mars. This was the sequence that we wanted to go through. All the landers go through this first sequence here. It's only the end that can be different. Yeah, the Americans tonight are landing with a completely different technology. Here we were going down with retro rockets, and then the last meter we would just fall onto Mars. This time, differently from Beagle 2, we decided to do all the possible observations from ground, from TGO, from Mars Express. Even the NASA spacecraft were ready to observe, but this time after landing, in order to learn from this landing. And these were the signals we were getting from the radio telescope, which unfortunately interrupted itself 50 seconds before the predicted landing time. Mars Express did the same. And in fact, what happened was that everything went well until the parachute deployed. And there the IMU, the inertial measurement unit of the spacecraft, saturated for less than a second. But this caused the onboard computer altitude estimation to deviate. And then the sequence followed. Later, this was predicted, was by a timer, jettisoned the front shield, the altimeter worked perfectly, but its measurements were ignored because the spacecraft was trusting more this, which was wrong. The retro rockets actually were activated, were working very nicely, but they were stopped by the computer 3 seconds later because the computer thought we were already on the surface. So the spacecraft fell from an altitude of, instead of 1 meter, 3.7 kilometers. And after 33 seconds, it crashed on the surface. As I said, failed landing, but successful test. We learned from it. And then the TGO, the orbiter, went on with its aerobraking maneuvers, which lasted 1 year. With aerobraking, you use the drag of the atmosphere to reduce the altitude of your orbit. And we went down from a very high altitude orbit, I don't remember now, it was 32,000 kilometers apocenter, down to an orbit, a circular orbit of 400 kilometers. Aerobraking is a very complex, operationally extremely complex exercise, where you basically change the attitude of your spacecraft twice during your orbit. It has to be in a specific attitude in order to maximize the drag when it gets close to the pericenter, and then it has to be Earth pointing up here in order to do communications and measurements. Sometimes you have to do a pericenter control maneuver because you want to increase or reduce the pericenter in order to be in the right range of thermal flux, of drag. And this makes the orbit even more complex. And sometimes you have even autonomous maneuvers, what we call flux reduction maneuvers. So the spacecraft detects that the flux is too high, it may damage the spacecraft, and then it commands a flux reduction maneuver, a slight increase of the pericenter by maneuvering here. And sometimes you have to do even an emergency maneuver commanded yourself. This is the planned in red and the actual in blue evolution of the orbital period. And these are all the delta V's that we got, about 1 meter per second. That was our target every orbit. And eventually, after 1 year, we had lost about more than 3 kilometers per second, and we were there. I've spoken mainly about interplanetary and scientific missions, but there's also an entire fleet of very important, very exciting Earth observation missions operated at ESOC. But operationally, of course, they are not as different from one day to the next and from one mission to the next compared to the interplanetary missions or the science missions, which are all quite unique. So they just keep going over an altitude of a few hundred kilometers. The challenges, operational challenges here are, for example, the in-orbit communications, which are extremely complex. We do it with optical links, with geostationary satellites. The high data rates, we're talking about here terabytes per day. This is Sentinel-1. The service availability, these are extremely tough operational challenges. And of course, the debris. You see here the population of debris, 1 meter debris, 10 centimeter, 1 centimeter, 1 millimeter debris. We're talking about hundreds of millions. And they are a problem. We have to maneuver to avoid these debris. Sometimes we are hit. This was an example of Sentinel-1 in 2016. And we have to live with this reality, which is getting worse and worse every day, especially if more collisions. This is a very dramatic model. More collisions will occur in the future. Sorry, this is the control room today. This is the table. Remember the table I showed you at the beginning? It's 1975, and look at the history of missions that we have flown. I took this picture in 2017. Now we've already started invading this side. It's a remarkable history of this center. We have a complex network of stations for interplanetary missions, for near-Earth missions, for launcher tracking, and we have a lot of missions in flight, 24 spacecraft at the moment, and many missions in preparation. And I want to show you in the last few minutes here the missions which are flying today. Bepi Colombo, launched in 2018. Solar electric propulsion, this time used operationally. We have 4 engines because we need 2 of them, so we want redundancy. And it's working marvelously. We have done 2 flybys. It's going to Mercury, and we need to do 9 flybys before we get there in 2025. Flyby of the Earth that you see here, this was April last year. Flyby of Venus, this was in October. And by the way, both were conducted during the pandemic, with most of the operations from remote, with very few people in the control room. We launched Solar Orbiter in February last year, another fantastic mission. Big challenge of Solar Orbiter is getting close to the sun, and therefore we have this heat shield. And operationally, the challenge is to keep the heat shield on the right side, because just deviating by a couple of degrees can damage dramatically the instrumentation behind, the rest of the spacecraft behind, which has to be kept cold. Solar Orbiter is also doing a lot of flybys. It has done already 1 with Venus in December, actually close to Christmas. And this one we've done actually completely from remote. We're getting really, it's becoming sort of a routine now, these flybys. In August next year, Bepi Colombo and Solar Orbiter will fly by Venus within less than 2 weeks from each other. And then eventually it will get to its orbit at the end of next year, at the end of the year, by another flyby of the Earth, and then use Venus during the mission occasionally to keep increasing the inclination and getting closer with the pericenter to the Sun. Another big subject, very important for tonight, is the Mars exploration. Look at the number of spacecraft which are operational today at Mars. 2 spacecraft on the surface, so many, also very old spacecraft, 2003, 2001, 2006, which are still very healthy around Mars. The newcomers, Hope and Tianwen-1, and hopefully tonight this new rover, in May or June, this new rover, and one day also the ExoMars rover that should launch in 2022. The target is to go to sample return, and in fact, before I get to that, I show you this plot. Fabrizio said it's nice to show how our people in the control center were summarizing the communication links for tonight between the lander and all the spacecraft around Mars, including the European spacecraft, and of course all the antennae on ground, including Russia and NASA and European spacecraft. So it's a very complex system of communications in order to follow this extremely challenging operation of tonight. The Mars sample return is the next frontier. In fact, Mars 2020 is the first part of this fantastic adventure, the landing tonight. Then this rover will go around and cache some samples, leave them around, and a new spacecraft will land with a European rover to collect them, with a launcher that will bring them back to orbit, and then another spacecraft, a European spacecraft in this case, will rendezvous with the samples in orbit and bring them back to Earth. A fantastic enterprise. Time is running out, so I go very fast through JUICE. For me, the most exciting mission of this decade is the Rosetta of the 30s. We go to visit the moons, the icy moons of Jupiter, and we will get there in 2030. We launch next year. You see the complex cruise with swing-bys of Earth, Venus, and Mars, the extremely complex tour of the Jupiter moons. We do 2 swing-bys of Europa, 13 of Ganymede, 14th of Callisto, and eventually we get in orbit around Ganymede. It will be arrival in 2030. You see the timeline here. End of the mission in 2033. But watch this space. This is going to be a fantastic mission. Comet Interceptor, recently approved. It's another great idea. We launch and we park a spacecraft at Lagrange libration point 2. And then when an interstellar comet or a long period comet comes, we are ready to go there and intercept it. We launch with ESA, we go into, finally, in fact, better late than never, into the world of exoplanet science. We have launched Cheops in 2019, and it's already operating, but we have 2 more fantastic missions coming out in this decade. So this is the decade of exoplanets for ESA. Of course, LISA, detection of gravitational waves in space. This is for the next decade, 2035 and on. And this is a fantastic technological challenge and operational challenge as well. Of course, Earth observation keeps keeping us busy. These are the future Copernicus Sentinels, which are in production at this stage and will start launching in a couple of years from now. And I want to mention also the Space Safety Program of ESA, which has various components. One of them is a very exciting mission jointly with NASA. NASA will send this DART mission to hit a very, very tiny asteroid which orbits another small asteroid. And we will launch later a spacecraft called Hera to observe the effects of this collision. And Hera will also carry 2 CubeSats, which will help the characterization of the asteroid and the collision. International cooperation is a very important aspect of our daily life in operations. Tonight is also shown. We support, though we have, of course, a minor role, but we support the landing of Perseverance on Mars. But we've supported the Chinese in their moon program. We've supported the Chinese in their arrival at Mars, and of course, we get support from NASA and from the other. Russia is supporting ExoMars and so on. This is fundamental in research, and we support also commercial missions. This is a Luxembourg-Japanese mission to the moon. So one day maybe this international cooperation will materialize on something, a permanent infrastructure on the moon. I'm through. 70 minutes was promised. This is my summary. Services, technology, knowledge. ESA is dedicated to this, and of course for Earth, for the solar system, and for the universe. And with the old picture of my Rosetta team, which I like very much. These are the guys who are actually doing the things while I'm telling you about them. And with a selfie of Rosetta, I finish my presentation, and I thank you very much for your attention.
Thank you so much, Dr. Ferri. We'll now hand back over to Fabrizio.
Yes, thank you. So you can stop sharing.
If I find out how to do it, I will. Yeah. Okay.
Thank you, Paolo. This has been great, and sorry for the audience. We went a little bit longer, also because of the hiccups we had at the beginning. And so I would like to, Paolo, I leave you 30 seconds to drink a glass of water so you can refresh yourself for a moment.
That's okay. Go ahead.
Yeah, we have some questions, and then I remind everybody we posted the link to join us on the Zoom meeting a little bit later. I would say that we can start at 9:15, 21. No, sorry, that's Italian time. It's 20:15 GMT for everybody, and then so we can have just a moment, and we plan to close this as soon as possible. So I go to the question immediately. If you have other questions, please post them in the Ask a Question link below the bottom of the screen. But please check if there are other questions satisfying you so you can vote them and we can process them faster. So we have one question that has been done even before you joined, actually, and it's been very voted by many people. Sorry. So with respect to the Rosetta Philae mission, it is known why the Philae terrain anchoring harpoons and reaction compensation thruster were not activated at the time of initial surface contact with the comet?
Yeah, that's a very interesting question. First off, I should say we, not being responsible for the Philae lander, we didn't have direct information about it, and therefore all the investigations have been conducted by the German Space Agency, which was responsible for the lander, for its engineering, but also for its operations. So I have information about the second part, the activation of the thruster. Before the landing, there was a safety valve that it was a pyro valve that had to be open, and this we didn't have a positive confirmation that this pyro had properly worked. So we were already quite convinced that this valve that would open the reservoir to the actual thruster valve that then would fire at the moment of the touchdown. We didn't have a confirmation that this safety valve was open, so we thought that this thing would not work. On top of that, I've heard that there were even other problems that may have prevented even the thruster valve to open, but I don't have direct information about it. But anyway, this was the thruster. And as far as the harpoons are concerned, again, I don't have direct information, but my understanding is that it's not clear. There are many theories, and about filaments being burned, about too high tension, about crossed wires. I've heard many theories, but unfortunately, we will never find out in reality.
Okay, thank you. And next one is, do ESA make use of NASA's Deep Space Network and vice versa?
Yes, we do. It's a very successful program. We call it Cross-Support Agreement for Network and Operations. It was established by my predecessor in 2007 for 10 years. I had the privilege to prolong it in 2017 for another 10 years. And both NASA and ESA are super happy with this. It gives us a lot of flexibility, and we use it practically with all missions. On top of this cross-support agreement, I mean, we use it tonight, for example, but on top of this cross-support agreement, individual missions have had and will have in the future agreements at the level of memorandum of understanding. So really mission-specific, maybe exchange between network support with science and so on. But the cross-support agreement is a much more flexible tool that allows us to set up a cross-support very, very quickly. And we do it with other agencies as well, with China, with Russia. It's very, very successful.
Okay, we are receiving a lot of comments for your presentation. Everybody's saying it's a great presentation. And please, Elizabeth, just for you to know, is there any way you can store the chat for future reference, maybe so we can post it and have it just in case? I'm just telling you. So the next question is from myself. Is there a museum where all the technology you used are preserved for historical purposes, like for example the wall display, spacecraft telemetry, or did they throw everything away?
Actually, no. Let's say there is not a museum. It's all left to individual initiatives, and like recently, ESA, in fact, was getting rid of a lot of spacecraft hardware, and they contacted museums, and they got things like the parachute of Huygens. So lots of things. Of course, not the real parachute of Huygens, the engineering model, perhaps. I know that there's a museum in Germany where we put some old workstations. I'm afraid the wall display of Exosat, I wish I had kept an element myself, but unfortunately I think it's gone.
Okay, and please do consider that the BIS has an historical archive in which also we have artifacts and things. So if you happen to stumble on something we can use, please remember we can try and manage this as an official donation or loan to the BIS, and we can use it as an artifact in our collection.
That's a very good point. Yeah.
So remember that. So yeah, this is okay. And the next question is from Felicia. Okay, Felicia. And what does a typical day mission control looks like?
Okay, it depends on the mission, yeah. But overall, one can say a typical day of mission control is mission planning, where you sit in front of a computer which is not communicating with the satellite; it's offline, and you get all the inputs from the scientists or from the users of the spacecraft, from flight dynamics, which says, okay, you have to do a certain housekeeping maneuver or whatever, from the flight control team that says, oh, well, periodically you have to do these things and so on. You put them all together, you check the resources, you plan when to do the things, and then you populate a timeline of activities, which then somebody else, a spacecraft controller, when there is the next contact with the spacecraft, typically daily, but sometimes for interplanetary missions is next week, will cut out a part of this plan, translate it into commands, and uplink it to the spacecraft. So the flight control team mainly works on planning. Of course, what you do, another task is review the telemetry that you have received from the previous day, from the previous week, and see if there are issues. You do long-term performance analysis. And when there are problems, and this unfortunately happens quite a lot, then you have to intervene. And this is not a typical day, but it's quite frequent. And normally the problems don't happen during working hours. They happen during night and at weekends, preferably on Christmas.
Yes, and we know something about that. Thank you, Paolo. Please do, this is of course the question you wanted. We know that you wanted this question. Please do explain the Eureca compatibility issue.
Yeah, it's a very nice issue, and I have a long story about it. I try to make it short, but basically, it's a common issue in very rudimentary telecommunication systems. It's surprising that this was actually flying on the shuttle at that time. But basically, when you have telecommunication systems, you do not detect the zeros and the ones. You detect the transitions between the zeros and the ones, and vice versa. So if you do not have transitions for a long time, so if the spacecraft sends too many zeros or too many ones in a row, your bit lock, what we call bit lock, so the capability of the system to recognize the bits, gets lost. And this was exactly what happened with Eureca. Eureca was, in the beginning, when we were activating it, was sending packets with a lot of zeros because nothing was active. So there were no ones that said, okay, this thing is active, this thing is active. And if I remember correctly, longer than 64 zeros, the PI link, which was this communication on board the shuttle, would lose lock. We didn't know at that time because Eureca was a packet telemetry spacecraft, so the packets were coming asynchronously. But the problem started with that. The nice story is that for the retrieval, of course, we couldn't solve the problem. But what we did, we reconstructed with our simulator the entire operational sequence of the retrieval, the entire telemetry flow, frame by frame. We looked at them. I mean, I did it manually, looking at each frame, finding out when the frame was full of zeros. Then we recorded this on a diskette, on a floppy disk. I guess many in the audience don't know what a floppy disk is. I flew to the States. I played it one night. It was actually night because this simulator was very, very occupied. Together with one of the astronauts of the retrieval mission, I played it into this simulator, and the astronaut was there on her display, watching what was happening. And I was sitting there with my timeline and telling her, okay, now you're going to lose telemetry. And she would lose it because I knew the zeros were coming out. And then I said, now you recover it. Oh, and she would recover it. Thanks to this test, NASA trusted us. We hadn't solved the problem, but we demonstrated to them that we knew what was happening. We were in full control. So we designed a timeline that minimized the problem, but when the problem occurred, we knew exactly when it was and when it would disappear.
So you were working with the bit and bytes manually?
Bit and bytes manually, and Fabrizio, you know this.
Yes, because
this is the daily life of mission controllers, not when they operate, but when they investigate.
Yes, 30 years later, I'm still doing that. I did that last week during an integration test. It was the only way to see the telemetry.
Troubleshooting is always on bits and bytes.
Yeah. Okay. Thanks a lot. Next one is from Rodney. This is a difficult question. I hope I can read it correctly. New Norcia radio optics as a parallel with some major astronomical observatories. I understand the advantages of a CUDE focus for astronomy, but what are the advantages for S and X band uplinks and downlinks?
Oh, okay. This, first of all, I don't even know what a CUDE focus is, but certainly is not a question I can answer. If I knew what a CUDE focus is, maybe I could. But I'm not familiar with the optics, with the details of the optics and the various options. I know that, for example, NASA has a different scheme. So the optics are actually, not for all of them, for some of these antennae, they have the optics in the movable part of the antenna, while we bring that, so the full thing, including the receivers and transmitters, where we bring them down in the shroud, and we have movable wing mirrors, but I don't know the details. Sorry about that.
Okay. And we have a question from Olesia. As a non-EU citizen, because Olesia is from Olesia is Russian. How could I get involved or work with ESA?
Well, as a staff of ESA, that's not possible. We are constrained to the 22 nations which are contributing to ESA. But as a contractor, we have contractors from all nationalities, including Russians. They work for the companies that work for us. I mean, in operations, I'm talking about operations now, but it's true for ESA in general. But in operations, we have 75% of our engineering forces are contractors, are not ESA staff. 25% is the ESA staff. So that's the way, is to contact one of these companies and to get involved with them.
But even if she's Russian, can she do that?
I have Russian colleagues. Again, I don't know. You probably have to go through some confidentiality agreements and so on, but there's no problem.
Okay, Olesia, if you get in touch with me, I know exactly which are the best companies to do that. So just get in touch with me. I can provide you more information now that I know that we can do that. Okay, and nice to see you again. So this is a question for me that some people also apprise. So referring to the switch, the radio frequency switch, actually that is a waveguide switch, and radio frequency switch on XMM, which was very unlikely to fail. How much Murphy's law apply to your flight control experience?
Well, okay, difficult question, because Murphy law is there. And unfortunately, you have to plan for the worst case. You cannot exclude the Murphy law case, because if you exclude it, it will happen. So this was a typical example where, I mean, I have the piece of paper still on my desk. I don't have it now, but I kept the piece of paper that said it's impossible that the switch gets stuck in the middle. And it did get stuck in the middle. Eventually, we found out by reproducing it in ESOC, by the way, that it didn't get stuck in the middle in the way that industry thought when they said it's impossible. They thought of a mechanical stuck. In fact, what happened was that the command, the pulse, the electronic pulse that went to command the switch to move was too short. Instead of running something like 100 milliseconds, it was 5 milliseconds. So the switch did move, but then it didn't go all the way. That's what we reproduced in ESOC, and we are convinced that's what happened. Because in fact, when we sent the next command, it worked. So it was not mechanically stuck. Okay, nobody thought about that eventuality.
So that was an issue with the high-level command. So then that
yes,
was
correct.
Okay, and were there any debris hitting the spacecraft, even the smallest ones? How did you manage to avoid any hits when approaching the comet? The question is.
Okay.
Some changes.
Yeah, if we're talking about the comet, the good thing about Rosetta was we were approaching extremely slowly. We're talking about meters and centimeters per second. So there was a lot of debris. In fact, mainly actually very, very fine dust. Yeah, but we were never hit by a big boulder or something. We were afraid of that, and we saw some of them. But okay, the likelihood is very, very low. But we were surrounded by these little particles that, with the relative velocities around the Earth, would kill you. But it was no problem because our relative velocity was very, very, very low. Giotto, with a relative velocity of 68 kilometers per second, was destroyed, or not destroyed, but severely damaged by these very, very fine dust particles. They are like smoke particles, and in fact they removed about 2 kilos of the spacecraft mass by simply just scratching it away.
Okay, and yes, Giotto, especially the mirror of the camera was hit because there was a shield in front of the camera was rendered.
The camera was sticking out, so yeah,
yes.
It was destroyed.
I just tell you just a couple of comments I got on the chat at the same time. It's Rodney that make it the difficult question. The focus of the antenna says that apparently knows that the place because there is a very good pub just down the road from New Norcia. So I don't know if you've been to New Norcia, but apparently maybe you have shared a good pub at that place. And also we have a comment from our friend Stefano Zatti that I'm sure you know. He says that it's very interesting and do not underestimate the importance of security.
I was expecting this comment from Stefano.
Okay.
And unfortunately, he is right. Yeah. Unfortunately,
I remember everybody that Stefano Zatti did a very interesting lecture beginning of this year about security and in space, how complicated this now is getting a serious problem. There are many levels of security. It's not just a matter of the simple one people can think, but there are real risks in managing satellites. So the lecture is recorded on Crowdcast. If you're interested, you can find it there. And another question, you know that at JPL they used to eat peanuts before very risky events, like in the next hour. Does also ESOC have a similar habit, or is it not superstitious at all? This is from Alessio, our good friend Alessio. Which is
it's a very good question because, in fact, this is not I'm very superstitious. I always quote Niels Bohr, which was a sort of one of my idols. Is a very famous atomic scientist, and he was interviewed by a journalist, and he saw that on the house door he had a horseshoe. So he said, "Professor Bohr, how can a big scientist like you be superstitious?" And he said, "I'm not superstitious, but I'm told that the horseshoe brings good luck even to people who don't believe that." Yeah? So that's my attitude to superstition. I'm not superstition, but if it brings good luck, why not? So we have a lot of rituals, but there's not an established one, and we have used the one of the nuts for some of the missions common with NASA. But each mission brings up its own things. I had a tie that I wore in every critical moment of Rosetta. from launch to the end. And by the end, I tell you, it was not in a very good shape because it was 20 years, but I kept wearing it. There was never a critical phase where I was coming without that tie.
Okay, good. And thanks for mentioning the Bohr anecdote, because this is something I always tell, and you are the first person I met that also says the same thing about the hot show story. So how many engineers, technicians does it take to run an ESA deep space tracking network station? Is it really zero? This is again from Rodney.
Yeah, well, it's not really zero, but just to explain what happens is we operate all the stations centralized in ESOC. We have remote, of course, we have a local team of engineers and technicians, and they can operate locally, and of course they do it in some occasions, but they don't have to. So they work in case there are hardware problems. They intervene. They are on call in case there are issues, but they don't work shift hours. We have a shift position, 2 positions, in fact, in ESOC, and we operate normally the stations automated. We load schedules and the stations operate automatically. And these 2 people oversee the computers that actually are operating the stations from remote. And if there is a hardware issue or a critical phase, or you name it, a test or whatever, then the local teams are there to operate.
Okay, thank you. And final 5 questions. So there is a question that I tried to answer already, but maybe you have your opinion too. Does the Arianespace Vega, we like to think is the Italian Vega, but anyway, does the Arianespace Vega still have potential after the recent payload delivery failures? This is from Ryan.
Yeah, it was unfortunately these 2 failures, almost one after the other, were very, very, very bad. But the spacecraft, the launcher is a fantastic launcher. It's a fantastic design. The last failure has been explained. It was, as you say correctly, Fabrizio, it's a manufacturing issue. Whenever we have used, we ESA operations have used Vega, it has delivered our spacecraft in an incredibly precise orbit. So I see a good future for Vega. Unfortunately, this is a complex business, and sometimes mistakes are made. These mistakes should not be made. I mean, I'm not trying to minimize the issue. Especially the second one was a drama.
Yeah, that's
but no, it's a super reliable launcher. I can see a good future for it.
Yeah, thank you. I share your feelings, and I worked a little bit on the Vega myself also, so I'm very passionate about it. What are the current limitations of autonomous guidance and navigation for exploration missions, and why? This is from Helia.
Sorry, can you repeat, please? I was reading another question and I got lost.
What are... yes, there is another one that goes on top.
Doesn't matter.
Let me finish with this one. What are the current limitations of autonomous guidance and navigation for exploration missions, and why?
Well, okay. I would need a long time to respond to this question. But for example, at the moment, let's say the guidance and the autonomous guidance and navigation is limited to, for example, optical navigation for encounters of targets. For example, NASA did it with a couple of their spacecraft. They want to do it with DART as well. When you have hardly any time to react from ground, and otherwise, when you have reaction time from ground available, then it's, if you want, you feel more comfortable doing it from ground. I see autonomous guidance and navigation as certainly the next step. It's happening. There's been some guinea pigs, NASA missions. ESA is working on that as well. There were discussions to do it also for the predecessor of Hera, AIM, and I'm sure that is coming. So there is no inherent limitation. It's just a matter of gaining experience, gaining confidence, and doing it when it is necessary, because of course testing and validating a reliable autonomous guidance and navigation system is very expensive. If you do not have to do it, then you think maybe it's cheaper to do it via the ground.
Thank you. And this opens a huge discussion, because also the US approach to what they call fault protection, for example, is significantly, not really significantly, but there are differences from what we do in Europe.
Yeah.
But also then there are different companies, for example, APL, JHU APL, that does this wonderful rule-based autonomous systems. For example, the one of New Horizon. Unfortunately, a lot of these technology tend to be very proprietary. So there is not, they are not shared with others. So it's a little bit complicated, but there are a lot of options. A new question from Rodney. And differential one-way ranging requires simultaneous visibility from two ground stations, approximately 120 degrees apart. There are only short periods available. When does differential one-way ranging that you have significant advantage over normal range read and Doppler?
Yeah, actually, whenever you can afford it, and I mean, typically we have overlaps of 2 hours. That's the minimum we want in order to do proper measurements. And of course, it's very difficult to schedule because, you occupy those 2 hours. There's no choice. You cannot shift those 2 hours. It's the overlap between the two antennae. But from what I'm, again, I'm not familiar with the details of the correlation there, but from my experience is that you get an accuracy in the direction of the baseline of an order of magnitude better than what you get with the normal Doppler and ranging, in fact, mainly the Doppler. So if you can afford it, it is always better. Of course, we try to do it with a 2 hours overlap. If you have less than that, then the implications are different. You have more dirty data to discard and so on.
Thank you. And then we have the final one about Smart One. Did Smart One make any low altitude, less than 50 kilometers measurements before it crashed from Elisha?
Yeah, unfortunately, I cannot. I think so, but I cannot answer this question. I don't remember. As I mentioned in my presentation, I happened to be on Smart One responsible only for the last month of the mission, so it's not something that I have clear in my memories. I could find out, but I don't know when we stopped doing scientific measurements and pictures. I think that below 50 kilometers, yes, but I cannot be absolutely sure about it. I would have to find out in the reports.
Thank you, Paolo. So we finished the questions, and I would like to thank you for this wonderful lecture and discussion. I hope that you would like to share again with us your memories and things, and do another presentation whenever you want. We are
anytime.
Here.
Anytime.
And you picked up to 236 people this evening, so you are a record holder right now. And but of course, he is a BIS member. That's what BIS is all about. No, Alistair?
No, I hope the people are not disappointed. But I mean, things to tell. Of course, there are so many. Today, I tried to make a summary. I'm very happy to come back on this type of venues. It's a pleasure for me. Thank you very much.
I expect there'll be quite a few more questions, but we've got a few things to ask before we go on to the next move, which is the landing of Perseverance. But I must thank you very much, Paolo, for your fascinating talk and your detailed answers to the many questions. And thank you, Fabrizio, for introductions and also coordinating the Q&A. And of course, thanks also to Elizabeth for coordinating the evening behind the scenes.
Yeah.
With Fabrizio.
Sorry. Paolo, are you going to join us on the Zoom link?
Yeah.
So Paolo, for everybody, Paolo is going to join us during the Zoom link, and it will be more informal. So you will feel free to ask more questions if you want.
Yeah,
but let's keep a keep out zone during the landing itself. You can be able to watch it and comment. We will provide maybe some insight in inputs about this later on. So go, Alistair, sorry.
Well, I'm told the actual landing starts at about, or it enters Mars atmosphere at about 2045, doesn't it? GMT.
Yes, I posted that.
Yeah.
I just posted that. And the GMT, of course, you are talking, yeah?
Right. Yeah.
Yeah.
Well, all I was going to say was we have some more talks lined up with Fabrizio's help. On the 2nd of March, we have Dr. Tommaso Parinello from ESA Esrin, who's going to be talking about cryosat and the Aeolus side, and he'll be telling us what changes here on Earth we can see from space. And on the 17th of March, Francesco Castellini, I should say, from ESA ESOC, is going to tell us more about flight dynamics, dynamic operations. So it'll be almost a continuation of the talk you've just given, Paolo. So that could be interesting. I'm told details are already on the website and the latest issue of Spaceflight. Now, I'm still looking for papers for the 12th of April, Beyond the Moon. We have some fascinating papers already in. We're talking about fuel from asteroids, material processing, interplanetary spaceships and launching from the moon, cities on Mars, and religious beliefs. But what I really would like is more papers on the medical effects of radiation, extended flight, loneliness, lack of gravity, infection, and mental health. The Reinventing Space Conference on the 28th to 30th of June. All the papers, I believe, are now in and are being sorted into a program. So I think we'll just look forward to seeing you there. Now, on the Arthurs, just quickly to bring you up to speed, we've had 160 nominations for about 75 nominees. Thank you for all of those. And the books are now closed on that. They closed on Monday. And we're now going to get the 60 judges to actually decide on the 3 finalists for each award. And then they have to select the awardees themselves. So the prizes or the awards will be given out at the dinner on the 29th of June during the space conference in the QE2 Conference Centre in London. So hope to see you all there. And again, thank you very much for a great evening. And I'm going to let you get away and we can join Fabrizio and Paolo for the Perseverance landing. All the best. Thank you very much.
Yeah, so let's wait 10-15 minutes for that. 10-15 minutes.
Yes.
So 21:15. Thanks a lot. Thanks a lot, and it's been a great pleasure. Thanks, Elisa.
Thank you.
Okay, we'll see you then. Bye-bye.
Thank you. Bye-bye.
Goodbye for everybody.
Bye.
Bye-bye.